and I'll welcome everyone. So good afternoon, everyone. Welcome to today's Resilience of Autonomous Systems seminar. It is a great pleasure to introduce today's speaker, John Day, who is the manager of the Engineering Development Office in the NASA JPL Systems Engineering Division. And he is also the leader for the JPL Center for Autonomy. John has over 30 years of systems engineering experience, working on a variety of NASA projects, into which he provided key technical and managerial expertise to human deep space robotic observatory projects and programs. The list is very long. I'll mention some of them: Europa Clipper, Constellation, Mars Science Lander, Mars Reconnaissance Orbiter, Deep Impact, Kepler, and quite a few others. John is actively involved in advancing the theory and state of practice of systems engineering, and his particular focus is currently on enabling increasingly autonomous systems. So I'll pass it on to you, John. Welcome, and we are looking forward to your talk.
Okay, thank you very much, Radu. Appreciate that introduction. And thanks everyone for coming to hear me talk. As the title says, I'm going to talk about some of the challenges and opportunities in robotic space exploration. So this is very much a perspective from the NASA JPL world and the kinds of missions that we fly, the kinds of opportunities we see, and the challenges we face in pursuing increasingly autonomous systems in space. Okay, so I thought I'd start with the definition of autonomy. Lots of different people have lots of different definitions. The one that I've chosen to use here is from the NASA Technology Roadmap, which just basically asserts that autonomy is the ability of a system to achieve goals while operating independently of external control. I think it's a pretty broad but useful articulation of that. And then you can go from there and talk about, well, that requires things like self-directedness, that it can achieve goals, and that it's self-sufficient or self-reliant, that it can do things on its own. Now, JPL has used autonomy for our entire history of spacecraft. And I've got a couple of examples on the side there, but there's three main areas that we use it. We use it for our fault protection, so protecting the systems from hazardous conditions and responding to faults. So if a radio fails, we detect that and swap to the other radio and make sure we maintain communication. We also make sure that what we call the critical events work despite the presence of failures. So things like orbit insertion or the EDL, the entry, descent, and landing that you've probably heard about on the Mars missions. Those are things that have to go right. And so we build in routines and mitigations for things to go wrong during those things to make sure that we still complete the orbit insertion or we successfully do the EDL. And then more recently, we've been increasing the mission utility. So we've been able to get more science from our missions by letting the vehicles do more on their own. And so examples of that are auto navigation. So our rovers sometimes, once we've gotten comfortable and checked them out, we use an auto navigation capabilities to allow it to detect the terrain, self-identify hazards, and then work around those hazards as it's trying to get to a set point that we've given it. We've also done similar things with our science observation, where the onboard systems can detect anomalies or detect things that shouldn't be there environmentally, and then stop what it's doing and take a picture of that and then come back. And the scientists like that because then they get just the data they need from that, instead of saying, taking a lot of time of looking at a landscape and hoping a dust devil comes through. So this is autonomy, but it's not where we want to be. So, these are semi-autonomous systems. They still have a lot of ground control, a lot of operator interaction. But we know that we can increase the robustness of these systems. So we can increase the science return, which is paramount interest to NASA. And we can also expand the places that are available for exploration by increasing the nature and degree of autonomy. I should say too, as I'm talking, if people have questions, raise your hand. Radu, if you see that, you can stop me, or people can break in and ask questions anytime. That'd be just fine. So what do we mean by expanding the frontiers? So, whoops, there we go. So the missions I have here on the right side are kind of what we're thinking about. So we want to go places that are just not conceivable to do today. And when I say conceivable, I mean conceivable to do with adequate risk. Yes, we can think about putting submersibles in the oceans of Europa. We can think about putting crawlers on the surface of Enceladus, or balloons in the atmosphere of Titan. But to do that in a way that has the ultra reliable aspects that our NASA missions need is going to require a lot of work. And so we're looking for our systems or vehicles that we deploy to be extensions of ourselves. I mean, these are our proxies going to places that we can't. So we want them to be able to do things that we would do if we could send humans there ourselves. So for space missions, we have certain characteristics that are sort of cross-cutting. And these are the kinds of things that we have to deal with all our space missions to a greater or lesser degree. First off, these are long distance. We're sending vehicles a long way away. So the timed communication takes a long time. It's very distant. The farther away, the less communication capabilities you have. It's just physics. And so it gets very difficult sometimes to have high rate communication with these vehicles. You have to be very, you're not going to be able to do joysticking of a spacecraft when it's at Saturn, for example. JPL and NASA, we're here to explore the planets and explore the solar system. And so the nature of exploration means we have little a priori information about the destination. As we send more vehicles to Mars, we of course build that up. But if we go to new asteroids, or if we land on the surface of Europa, or we send vehicles like New Horizons into the Kuiper Belt, we're sending our vehicles into places where we really don't have a priori information. So it's harder for us to use techniques like machine learning, where you can build up a training set, because we just don't have enough information to build a good training set. Our missions are infrequent, so everything we do has to be ultra reliable. We send a spacecraft to the outer solar system once every decade, maybe once every couple of decades. So if it goes, it's got to work. So that requires a lot of testing, a lot of upfront work. It also tends to lead us to relying on solutions that we know currently work. And so one of the challenges we face is developing high reliability solutions that are evolutionary from the prior missions and take advantages of new technologies and that sort of thing. One problem we have is that that's different from terrestrial applications, is that everything is tightly coupled. We are very mass and power constrained on these systems. It takes a lot of energy and rocket power to launch them, and so the smaller they are, the better. That means that you have coupling between different sorts of state domains. So your thermal state affects your power state, which affects maybe how much energy you have for computing, which affects how much resources you can apply to turning the spacecraft or sending data back. So these are all things where ideally, in an engineering way, we would decouple them and provide ways they wouldn't have to interact. But just the nature of our systems and some of the other constraints we're dealing with means that those are all tightly coupled. And so our control algorithms have to be aware and account for that. The next point here is obvious. Once we send them away, there's really no opportunity to maintain them. We can send new software uploads, but aside from that, the hardware's got to work. And if something fails, then it's broken and we have to find a workaround. And the last thing is something that requires us to rely on analysis. When we send our vehicles to Mars, for example, you've seen the entry, descent, and landing with the parachutes and the pyros and the whole suite of things that happens. When you see that, that's happening for the first time. Parts of that have been tested independently, but that whole arc of activity only happens the first time that the mission runs. And so we have to do a lot of analysis and have to have a lot of confidence that that mission is actually going to that series of events will unfold in a highly reliable way as it goes through the first time it arrives in this environment. We also have different modes of science observation. I won't spend a whole lot of time on this chart, but just to give you an idea, we have missions that are sort of more observatory style. So this is a picture of the upcoming James Webb Telescope. It's basically, it could be an Earth orbiter, it could be an orbit around the sun, it could be at a Earth-Moon Lagrange point. But they basically are one spot, and then they are looking at a variety of targets far away. And those targets are generally static. Then we have flyby missions where we're sending, in the picture here is a Voyager, where we fly by a target. And so it's similar to observatory in that you're flying in a fairly, your relative motion has now become a factor between you and your target. And so sometimes the flybys are very fast, and so you have a critical window there to get your science. And so that becomes something that has to be protected. And so a lot of our fall protection is built around making sure, say, a flyby proceeds accurately. Then we have orbiter missions. We have orbiters around Mars. We have orbiters around, had an orbiter around Saturn. We have orbiters around Jupiter right now. We've had orbiters in the past around Venus. Once we get these vehicles into orbit, they settle into a routine set of observations, much like an Earth orbiting mission would, but just at a distance. And the last category here is in situ missions, which covers a broad variety of things, not just rovers. But these are more complicated because now you have a variety of different targets. You have a variety of environments and changes in your environment that you have to deal with. And the kind of planning you have to do is on an increased pace because of those changes. So Radu, was there some questions in the chat?
Colin, would you like to ask your question?
Yeah, hi John. It's just a simple question really. You mentioned limited in terms of communications and computing power and the like. I wondered if you could give us a kind of a little snapshot of what that might mean. You know, what are our bandwidth and our delays on communications, and what computing power could we reasonably expect to have on a platform on Mars?
Yeah, so in the communications era, we're limited by the speed of light. So to Mars, it's between like I think 9 minutes and 20 minutes, depending on the where we are in the orbit. For Saturn or for Jupiter, I think it's on the order of 1.5 hours each way, and for Saturn, I think it's on the order of 3 hours each way.
Okay. Okay.
And we're talking about transmitters on the order of 20 watts, or maybe even 50 watts. So that's why we have the big DSN dishes and why they're so big, because we're trying to catch those very small signals. So we're getting really great communication back from Mars right now because we have several orbiters that we can help handle that load. And those orbiters have big antennas that they can send back information. The Cassini mission that we sent to Jupiter, its highest rate downlink was about 100K downlink. And that was for science using the science antenna. If we were using the engineering antenna and we didn't have access to that, it would be more like 5 or 10 bits per second. So it can get very, very limited. The state of the practice in the processors is something that's called the RAD 750. It's the same PowerPC processor that you had in your Macs in the 90s. But that's it's been space hardened, and so that's what we've been using. If any of you have been following the Ingenuity helicopter on the surface of Mars, it's using actually a Snapdragon processor, because that was the thing that had enough computing power and was light enough to go into the helicopter. So one of the big things that about that flight and about the use of Ingenuity is using a commercial processor on Mars and seeing how it works. And so far it's worked beautifully.
Wow. Yeah, fascinating. Thanks, John.
Okay, I'll keep going. Okay, I'll spend a little bit of time on this chart just because there's a lot of stuff going on here. But one of the ways that we are thinking about this is how to make a case, or how to describe some of these characteristics and how we ended up with the missions we have. So if you think of a two-dimensional picture where you have communication on one end, where at the short end on your x-axis here, it's short delay, you can have lots of communication opportunities and unconstrained bandwidth. So that would be like an Earth orbiter, or it's some sort of teleoperated vehicle on the surface of Earth here. Whereas the other end here is the long delay. So, the Voyager spacecraft that we've sent out, I think it's 17 hours one-way light time to talk to those. So you have very little opportunities to make communications. And then if you think on the y-axis as what's the dynamics that you're trying to work with, either the dynamics of your system or the dynamics of the environment. And you can have things that are static and well-known, like a trajectory, or you're at a specific place on a planet, that's not changing. Or you have things that are fast changing and unknown, like the underwater systems I mentioned before. So if you think about that, and this is notional, this isn't mathematical at all, you can think there's a controllability threshold here. So if you, even in a fast changing environment, if you have lots of opportunities for interaction, you can do ground-based planning and open loop execution in a low risk way, because you have the opportunities to correct. Whereas if you're over in this part of the regime, the ability to project your conditions with confidence is uncertain. And so the use of ground-based planning and open loop execution becomes a high risk way of doing the mission. So when we think about doing autonomy, we look at what are the things that are changing, what are the things that are uncertain, and how do we reduce that uncertainty by adding control loops to the process and adding decision making. So past and current missions kind of operate in this regime here, where we try to keep as much of the humans in the loop as possible, because that's what we trust, that's what we know, that's what we have relied on and been able to be very successful with in the past. But a lot of the exciting things that NASA wants to do in the future are in the other side of this. And so we've got to figure out a way to make this paradigm shift so that we start allowing the vehicles to have more and more decision-making capability and have some trust in that capability. So some of the capabilities that we look for in general kind of fall into these four categories. I'll start with the bottom here. We talked about high performance computing. The computers we use are 20-ish years old, so that limits the kinds of things that we might think about doing. We'd like to do things like, neural nets and self-training systems and things like that, but we really have to have the computing power to make that happen.
John,
real-time adaptation.
We have a
John,
question from Jeff.
Sorry, John. Thanks. It's really riveting listening to this, and I have to say what's been achieved is actually so impressive. But one of the things that I want to understand from what you're saying in terms of these uncertain conditions that you're hoping to be able to deal with are you saying that up till now you've not used planning or planning synthesis or controller synthesis in the existing software that actually is being used for by NASA and for these like the Mars missions? Is that the case, or is there actually online planning going on?
So there's the vast majority of what we do is we call them time-based sequences, but that's not quite exactly what they are. But basically, all of the planning is done a priori on the ground, and there's very little ability of the systems to deviate from that. When I mentioned having more mission utility on some of our Mars missions, what we've done there is add some very simple scheduling on board, where we give it a set of tasks to do these tasks. And then we give it a queue of things. If after doing those tasks, you have extra power, time, or energy, do these tasks in this order. So it's very limited. It's something that the ground team can assess and have confidence with. We do a lot of technology research into, correct by construction controller synthesis, plan elaboration, that kind of thing. There's been some field tests where we've done some of that work, but that's we're still working on bringing that into our flight projects that we fly.
Okay, that's very interesting. Thanks very much.
Yeah, of course. Let's see. So yeah, relevant to your question, we want to get to the point where we have real-time adaptation, where we can, the plans are, we've given these systems high-level goals, and then they can elaborate the plans and do some backtracking and do that in a way that's aware of the potential risks and the resources they have available. This over here on the right, feature detection and data interpretation. One of the things we say is that we usually have a very thin straw of data coming back from these systems. So the more data processing we can do on board and send back just the results of the observations, not just the raw data, the more information the scientists will be able to get. And we're looking at different ways of doing that and making that trustworthy. One way is to build a lot more memory on board these systems, so you retain all the information, but you do data processing and send back the processed data, or just the the deltas in the data or something like that. Some data processing and data reduction activities, but you keep all the raw data in case somebody wants to go back and ask for that later and get that. So there's things like that we're looking at. We have a whole robotics group at JPL who's looking at trying to make sure that wherever we go, whichever in situ mission we're working on, that we can have mobility on any surface, and that we have dexterous manipulation, that we can have dig into an unknown set of snow on the surface of Europa or ice, and know whether or not that's been successful, and whether a second need to go again, or a third time, or a fourth time, and when maybe that's not going to work and you need to try a different area. So there's things like that of trying to get those decisions made on board in a trustworthy way, because otherwise it just takes so long to do these missions that in some cases doesn't become worthwhile. Okay, so on the development and application challenges, I mentioned some of these before. So we have the physics challenges before, and these are sort of the development ones. I mentioned before that we have infrequent missions. And so that results in, it makes it very difficult to learn from your successes and your mistakes, because you've got to learn from that, get that into your processes and cultures, and then use that, say, a decade later. So it becomes it's not like we're doing this like a car company where you have a new version coming out every year, and you can, if something doesn't work quite right, you can fix it or do a recall or whatever. So it's something where when we learn something, we have to make sure that it gets infused into our processes and our culture, so that we don't forget that the next time we do a mission. Right now, our implementations, because of various reasons, it's time consuming to develop and difficult to validate. I mentioned before that they've got to work exactly right the first time they get there. So that involves a lot of analysis and testing to make sure that's the case. Related to that are challenges that we have in designing, certifying, and operating these missions. These are challenges not so much in, it's just the nature of the problem. In sending these places, you could have things go wrong that you didn't anticipate. So you've got to have a savvy operations team that can help you work through that. If we start giving more authority to the vehicles, we've got to be able to shift that and make sure that we can give it the opportunity to make decisions when it's safe, but you got to be able to pull that back if something unusual or unexpected happens and you need some help from the operations team. Currently, we're doing a lot of technology work and engineering process work using models, including model-based system engineering. But taking that and translating that into behavioral models that could be reasoned about on board is something that's still in a research phase. It's not something that's made it into our flight projects. And the last bullet here is just that, I think I touched on this before, but we really want to be able to use more capable computing platforms because that just opens up the suite of things that we could do. And otherwise we're limited by solutions that we can deploy. This is just a page that one way that we're thinking about how to get there, because we have all of this great research and we're like, okay, how do we get this into our systems in a way that doesn't risk the science that we're trying to perform? And so we have this idea of an iterative loop, that gradually increases the capability as we go, and 3 evolutionary stages of capability. These are notional, but it'll give you a sense of what we're doing, and what they're kind of based on is what kind of instructions do we give the vehicle. And so we're at stage 0 now. Generally, there's a few exceptions. But stage 1 is what we would call a resilient system. It's a system where we give it a tactical plan, so a well-developed plan, but we allow it the opportunity to adjust that if resources or faults happen and we want to work around that. And so we give it a little bit of ability to adapt that. We think to do that, it'll have to be able to use its own models of internal state and do some reasoning to figure out how to work around that. We want all of the control that's on board to be done by closed loop commanding. A lot of the control we do today, sort of the stage 0 stuff, is open loop because we can predict in advance what's going to happen. As we move into this regime where we can't do that, we're going to need much more closed loop control. The next stage is something that we might call an independent system. In this case, we give it a strategic plan. So here are your science goals for the next 2 weeks. And then we allow it to develop its own tactical plan to accomplish those science directives. And when you start getting to this point, an observation of someone on my group said, at this point it becomes more of a negotiation instead of a direction, because you might tell a vehicle, I want you to do this. And it can say, well, I can't do that, but I can do this and this and this. Is that okay? And so there becomes a back and forth in the planning process that I think is going to have to happen as we start getting to those cases where we're giving higher level abstractions in terms of the directives we give to the vehicles. If it's an in situ vehicle, then it'll also have to use models of the environment as well as itself to be able to do this kind of reasoning. And the last one is really more of an aspirational stage, but if you sort of take this analogy to the end, you tell it what hypotheses you'd like to support or refute. and then it develops a set of science measurement plan that gives the scientists the data to be able to assert or refute those hypotheses. So that's kind of a way out there kind of thing. But at this point, you can kind of see the way we're handling it at the resilient system level. We're giving it detailed plans and it allows some adaptation. Independent system, we give it some strategic plans in terms of science objectives. It develops a tactical plan. And the last one is more of a find data that's going to help us resolve these hypotheses. And then it does the rest, given a suite of instruments.
So John, do you think explainability might be a problem at stages 2 and 3? Because you'll need to trust the system, but to do so,
yes,
you need some evidence.
Yes, absolutely. And that's something that we're looking into. The last one, like I said, it's much more of an aspirational kind of stage, but the independent system is something that I think is something we're actively looking into. We have to be able to get enough information back of why did you choose that plan? What were the alternatives that you considered? And why did this plan rise to the top? We're going to have to be able to ask questions like that. Another thing that we're looking at, and we haven't gotten too far into this, but the idea of building layers in our control structure that mimic in some ways our limbic system in humans, right? So when you go out for a run, you don't have to think about increasing your circulation or breathing heavier or anything like that. The rest of the system takes care of that and then lets you accomplish, your exercise. But it also keeps you from overheating or getting too cold or running too long, right? So if we have a limbic system that's a part of this control architecture that maybe prevents self-damage, then that's another way to gain trust, because it's a more scoped problem. And then if you layer on top of that, activity planning, then you can have some confidence that whatever the activity planner comes up with, which could be a very complicated and maybe not fully explainable, you have confidence that you're not going to harm the vehicle with any activity plan that you come up with. So there's a few different ways to look at that. And if you guys are looking at some of those, we'd be interested in hearing more about it as well.
John, I wonder how much you feel that appropriate models play a part here. So I'm thinking about the idea of capabilities of the machine. So I was thinking about the idea of, I want to get from A to B. I know that I can navigate. Maybe I've got the ability to move things. Maybe I've got some manipulators on board that allow me to move things. But that's very much a case of me defining a priori what a set of capabilities are. And at what stage along this you move into the fact of this capability discovery. So there's various things that you say that we find we can do, or we find we can't do. I remember you telling us at another meeting we were at about finding out that the wheels had become shredded on a rover, and suddenly discovering
right.
capabilities no longer existed, and kind of how that kind of modeling and discovery would fit into these different stages.
Yeah, I think that's a really ripe area for research, especially sort of the discovery aspect of that, because to do that fully requires the ability to not only start with a world model, but to adapt it over time. And I think that's a very difficult problem. But something well worth looking into, because so where we're starting with that is that we're starting with, well, how do we develop appropriate models of behavior for internal behavior, and how can we leverage those to work around things? So as an example, you might have a camera, a science instrument that requires preheating before it works well. Well, what happens if that, if the preheater fails? What are you going to do about it? Well, maybe you can turn on something next to it that's going to keep it warm over time. So you have to have those relationships explicit so that a reasoner can start making those connections and say, I have, these different ways to provide heat to this box. What's the most appropriate way to provide heat to this box? And the next stage after that is that inferring new relationships as the world changes. And I think that's going to take some discovery and I forget the phrase. It's going to have to make some hypotheses about the world around it and come up with solutions and try out different things. And that may require doing some things to get that information you need to build and adapt and validate the models that you're trying to work with.
Yeah, and even explicitly invalidating assumptions that you'd made at design time.
Yes.
Very challenging. Yeah.
Yeah, I think the trick though is the models, right? I mean, you've got to take the time to make the model, because only then can you start doing this kind of reasoning.
Yeah.
One of the things we're doing right now is taking some of our we've done some work in some model-based diagnosis, and so we're taking those algorithms and we're bringing them into our integration and test flow. So when we run a piece of hardware through its tests, we run the same inputs through this automated diagnostic test. And so if something doesn't go right, we have an automated way of giving us an idea of what might have gone wrong in terms of location. It's really a fault location algorithm as opposed to a diagnosis, but it tells you where to start looking. And so things like that, where if you start using models during your integration and test, then that's one way of validating them so that you have solid models to use when you're doing reasoning on board during flight.
Yeah, thanks, John.
Okay, so I think this is my last chart, but we're on a path where we're planning and pushing to increasing the nature and degree of autonomy in our systems. This is necessary in order to expand the frontier of robotic space exploration. Unless we're satisfied with the exploration we've done today, we need to sort of go across that boundary that I talked about before and get into this space where vehicles can be self-directed and more independent, but in a very highly reliable way. And if we're able to do that, then we can increase the robustness, we can increase science return, and we'll expand the opportunities for exploration. And this isn't something where there's an end state we're shooting for. We're shooting for a place where there's a continual evolution. And with each step in the evolution, we are able to accomplish more and more and more. So it's not an end state we're shooting for. It's this evolutionary continual improvement. And we know as we go through this that we're going to need to leverage work that's happening all around the world. Artificial intelligence, machine learning, model-based systems engineering, software development technologies, and just advancements in robotics. I mean, you see things like what the Boston Dynamics folks are doing in the US, or you see the things that are happening with the ESA OPSAT, for example. These are all ways of exploring technologies and finding new ways. There's so much investment going on in these areas that it's something where we really want to try and pull that in and apply those technologies and approaches on our particular niche area here, and take advantage of that, of all that work that's going on. So with that, I'll stop, and then we'll have some time for questions.
Thank you very much, John, for a most insightful presentation. We have a question from Tim. Would you like to ask your question, Tim?
Yeah, can you hear me?
Yes, we can.
Yes.
Yeah, John. It may be a silly question, but go ahead. To what extent has onboard model calibration or error map generation actually been used or explored? Or is the actual plan to use feedback loops to remove the demand for that?
So we have, I'll start with what's currently being used. So the places where we use a lot of onboard closed loop control are in our pointing systems. So just the attitude control of our systems and knowledge. So that's where we have the case where all we do is tell it point the high gain antenna to Earth, and then it takes care of the rest of that. It does the rest of the vector propagation, those kinds of things. And we do a little bit of that with some of our motor controllers and like the wheels for the rovers, Kalman filters and the motion of the arm and those kinds of things. So those are things that are being done now. But there's not the onboard system to a large degree outside of those areas doesn't have an explicit goal given to it. It's more everything is more procedural than declarative. And so I want to move into a regime where it's more declarative, where it's like, we want you to do this at this time, or be at this spot by this day. And then the system is able to safely figure out a way to get there, or tell us that that's impossible. So I don't know if I've answered your question directly, but we tend to keep things on past missions. If we can do it on the ground with operators, we tend to do that. And where we can't do that, then we've given the system the ability to do that. But that's only been done in cases where there wasn't a way to do it from the ground. But that's the paradigm shift that we need to sort of move past to get these systems that we envision in the future. Did I answer your question?
We cannot hear you, Tim. You are not muted, but still we cannot hear you. No, now it should work.
Thanks, John. And yeah, really fascinating. Discussion.
Right.
Thanks.
Thank you. So Elias, you wanted to ask a question?
Yes, fascinating talk. Thanks. I was wondering, you mentioned about software uploads that take place. So are you actually using those in some missions, and could they be a technical way to support new capabilities?
Yes, absolutely. So a good example of that is our Mars missions tend to last a lot longer than the original mission. And so for both the MER rovers in the 2000s, and then the Mars Science rover on the surface now, they're both in their extended mission phases. And so what happens there is that the primary science has been accomplished. And so NASA usually allows us to do more things with those rovers than we had in the past. So one of the things we did early on is that we added dust devil detection to one of the rovers, so that when it was taking pictures for, it would take pictures, for example, for the path planners and the navigators to figure out where to go next. Well, it left those cameras on longer, and then if a dust devil showed up, then it would start recording that dust devil. And so that's how they got recorded some of the dust devils. And then there's a system called Aegis where it was actually used to, one of the things that they do with the cameras is they use a little laser to zap the rock and then use a spectrometer to see what the composition is. But they would aim it with just mechanical accuracy. And what they were able to do is to add some software that would take a picture before it did a zap, and then it would do a little self-adjustment. So it would always hit the right point every time. And so it's things like that where we can add capability to the missions afterwards. And we've done that several times, or we find something that is wrong, right? An algorithm doesn't quite work the way we expect, or that kind of thing. So we update the software and then go forward.
Fascinating. I was the wrong case. I thought that might be happening, but you actually said here that also kind of repurposing or calibration happens this way. It is nice. Yeah. Thanks.
I have a question as well. Maybe you go first, Jeff. Shall I? So I wanted to ask John whether, in addition to fully autonomous systems, you are looking also at autonomy, human teaming.
Yeah, absolutely. And that's a good point that I didn't talk to very much, but any autonomous system is really a combined system of machine and operators. And I think one of the challenges we have at JPL is we're used to a certain mode of operating vehicles. And we're looking at ways of shifting those responsibilities. Some of the technologists we work with use the phrase, instead of humans in the loop, humans on the loop. So humans in a more monitoring capability, but that they could that the mechanisms are in place for them to step when it's required. So yeah, it's definitely something that has to be part of this thought process.
Thank you, John. So Jeff and then Colin.
Thanks. I have to say I'm absolutely fascinated by the not only the way that you've done things, but also I think the resulting successes, which is very impressive. But I'm still trying to get a feel for where the limits are and how much you do, let's say, automatically, and how much is done, as you say, with humans on the loop. Presumably the models that you have and that you use and that you intend to use and put into the running, so for reasoning at runtime, essentially online, these would be behavior models that you actually develop on Earth. You develop a priori, and you develop these and make sure that they work and so on, and then these would be the ones that would be loaded and enhanced, hopefully, by learning in the field. Is that sort of the intention there?
That's definitely where we want to head. Right now, most of the models that are on board right now kind of fall into two categories. So there's activity-based models where we load up a set of activities that have defined, say, resource requirements. We need these 3 pieces of hardware to be healthy, and we need this many watt hours of energy available to perform this task. And then, we have this, like I mentioned before, we have this onboard scheduler, which can schedule those tasks to work out. We've had missions in the past that have done a lot more. Radu, I can send you some links, but if you look up the EO1 mission or the EO1 science craft, it was an Earth observing mission that in its extended mission, we were able to put a full planning system on board that did a lot of different things, including detecting volcanoes and floods and that kind of thing. And operation on that particular system was completely autonomous. There was actually nobody in the control room at the end, because it could handle itself unless something went wrong, and then it would stop and raise alarms and that kind of thing. But you know, that kind of level of autonomy we haven't shifted into some of our other planetary missions. The other kind of models that we have on board are really implicit in the software. So, you know, Kalman filters and that kind of thing in our point and control systems. You know, some software controlled thermal conditioning, that kind of thing. And what we really want to move away from is to make those models as explicit as possible, so that we can reason about them. And the reason is to build resilience into the system. We're going to have to be able to reason about that in a way that doesn't require either people or the machine trying to figure out what's in the code. It's much easier, and it's much more straightforward. I won't say easier. It's much more straightforward to reason about a situation when you make all that explicit, and you have separate models from reasoners, and then you can have. And so we're working towards that, but that's very much a topic of research, and not something that we're ready to deploy.
Thank you. That's actually very informative. The second thing, if I can just briefly say, you talked about these you know, stage 1, stage 2, stage 3. I think in the future and so on. It actually has a lot of reminiscence of the kinds of systems that we try to look at in the approach to adaptive systems, where you'd have the lowest layer essentially as a resilient layer, which is looking after itself, doing the fault tolerance, fixing anything which needs to, and then running the system. And then if necessary, what happens is, if that actually doesn't succeed, what you need is a new plan. And that new plan has to be either an existing plan, which with the layer above would actually have to come up with, provide, make sure that the capabilities are there, and then pass down to the resilient layer, which then works on that and so on. And then you seem to have this highest layer, which says, well, if I have these much more vague notions of what kind of research I want to do, and I need something which is going to generate hypotheses, I need to then say what kind of plan would prove or disprove that hypothesis, push that down to the next layer, which actually says, okay, here's a new plan. Do I have the capabilities to do this, and so on? And then if there's actually a capability, then you go down. So this layered stuff, I find anyway, I have to say, very appealing, and very much a view that I think is now being discussed quite widely in the sort of adaptive systems world. So that's just more a comment, and yeah, I find it very appealing.
Yeah. No, I appreciate that. And you know, there's people have talked about 3-layer architectures for a long time. But you know, I think you've hit on something there, that the kinds of capabilities that I described there might have a pretty tight mapping to some architectures that you might use to create those things. So yeah, no, I like that insight.
Thanks very much.
Colin?
Thank you. Just on what Jeff just said there, I wonder if there's also something about minimal change. So how little can you change a plan might be a way of considering as you go. I was following on from what Ilias said earlier. It made me think that as we send more vehicles with different capabilities up there, whether we're hitting a point where we could potentially send agents up with the explicit intention of overcoming the limitations of certain vehicles and working as teams. Because obviously we don't want to send up a massive new robot with all the capabilities of the other one because of the weight problem, if actually just adding something new on the ground could help. Is that something that's been considered?
I think let me answer your question 2 ways. So we are looking at multi-vehicle solutions, whether it's, a small constellation or maybe swarms of vehicles. The CubeSat costs are coming down dramatically. So it becomes much less, can starting to become cost effective to send a lot of vehicles, and you can get some redundancy that way. I mean, the Starlink system that SpaceX is putting up is an example of that. I think they've had something like 3% attrition already, but there's so many vehicles, it just doesn't matter. So that is an area of active research at JPL, and we're doing some work with our colleagues at Caltech on that, on how to control vehicles like that in a safe way. The other thing that we haven't solved this problem, but it's of interest, which is what we're tending to do now is to not think of, well, we have this vehicle and we have this ground system. We're starting to mash it all together and think of it as a complete architecture. And so the question then becomes, okay, how do you architect that combined flight ground system in a way that you can transfer functionality amongst different aspects of that, in particular from the ground to the flight. So, and you change those interfaces along the way. But I think that's it's a challenging architectural and software implementation thing to be able to do that. But I think that's something that we're very interested in trying to do, because as our missions, as you might imagine, we launch our spacecraft. They sometimes spend a long time in a very boring part of their mission where nothing's going on. I think it's very exciting when it gets to this destination. So you can envision that you would have maybe a lot of ground control during the boring period, and then you might want to assign a lot of those capabilities back to the vehicle when things get exciting. So over the course of the mission, you'd want to have some of these changes in where functionality is being performed, just as a part of doing the mission. And then you might want to be able to change that as things happen later. You want to, maybe you gave all the fault detection and recovery responsibilities to the vehicle, but maybe you want to pull some of that back or give it more of that. So you want to ideally sort of have this ability to, in a frictionless way, move functionality around. But that's a tough problem. We haven't, we're thinking about it, but we haven't cracked it. So again, if you guys have ideas along those lines, we'd be very interested in hearing about them.
Thank you.
All right, I think we have time for just one last very short question, Elias.
Okay, very short. I was wondering, in the end, why do you want to make the missions more autonomous? Is it the resilience you want to build in? Is it something else as well?
It's there's really three things, and ultimately maybe five things. So it's ultimately we want to get back more science, and that's what it comes down to. So if we want to do science in places where we can't predict the environment days or weeks in advance, it becomes risky for us to use current techniques to do that. So to expand the frontiers of where we want to go, we have to develop more of this closed loop control on board. So that's part of it. And even with, so that's sort of flipping over into that other part of that two-dimensional chart that I showed earlier. But even within that lower quadrant, we can do more, and we can make systems that are more resilient. You guys might remember the Galileo mission to Jupiter in the 80s. When it launched and it was heading out to Jupiter, it had this really huge antenna that it was going to open up and send back a huge amount of information to Earth. Well, a couple of ribs on the antenna stuck and it didn't open. And so the engineers and the scientists had to figure out how to do an entirely different mission where the data coming back was a couple of orders of magnitude less than they expected. So they were able to, because the onboard computers were designed in a way to, we could change the software. There was enough capacity, extra capacity in the processors and in the data transfer between them. They were able to add things like really intense data compression and co-processing of data, and they basically rewired all of the software in that system, but that was enabled because there was enough hardware resilience in the system to do that. That's hard to make a case to put into every mission because it's because of the cost constraints and the size and complexity constraints. But generally, the more resilient we make our spacecraft, the longer they're going to last, the more that we can do with them. So, you know, this resilience, robustness aspect is very important for us. We can't just rely on large margins and over designing spacecraft going forward. So the more resilience we can build into the software, if we get to the point where we can trust that, then it's really going to open up, I think, a lot more science, even in that lower quadrant, as well as allowing science in the upper quadrant.
Yes, thanks a lot. Yeah.
So I'm aware, John, that you have another commitment. So I'd like to thank you very much again for giving this insightful seminar, and also thank you everyone who attended, asked questions, participated in the discussion. I'm looking forward to seeing you in 2 weeks' time at our next seminar.
Yeah.
Thank you very much. I appreciate your questions and interest, and look forward to seeing some of you again.
Yeah, thanks, John. Great talk. Very interesting.
Okay.
Thank you.
Thank you.